Hello and welcome back to the breadboarding tutorial series. In a previous video we discussed how to use the multimeter as a voltmeter, ammeter and ohmmeter, and in this video we're going to be discussing series and parallel circuits. So before we begin, just quickly to note that a series and parallel circuit are the most simple circuit designs that you can make. If you do not know how to make a series or a parallel circuit, the rest of the circuit building becomes very difficult very quickly. In addition, almost every single circuit that you make can be modelled as a series circuit. This is useful later on, but for now it's just a side note as we pass over it. So, with all that being said, let's move over to the video. So we're going to begin with a series circuit. As you are aware, a series circuit starts with a simple voltage supply, and then we need a load. We're going to use 3 resistors. So I'll quickly sketch out what it is we're going to be making. So here's our 5-volt supply, which will be our Arduino board. And these are going to be 3 resistors, R1, R2, and R3. In a series circuit, if you imagine it like a traffic light system, when you get to the first traffic light, you have to wait, and then this takes up a lot of congestion on the road. Then some traffic is filtered through to the next one, where it meets another traffic light, then even fewer bits of traffic can get through, and then by the end there's no traffic getting through, and that completes the circuit. So there's a short graph that we can draw to demonstrate this. If this is the 5 volts that we begin at, we then hit the first resistor and our voltage comes down. We then hit our second resistor and our voltage will come down again. Then we'll hit our third resistor and our voltage drops to 0. So what happens on these little declines here is the voltage passing through the resistors. This small drop happens over a fraction of a second, so it's effectively instantaneous. We just need to know that there is in fact a decline. It's not just a sharp drop. This is what we call our potential difference. In a series circuit, you can effectively have one resistor that's equivalent to R1, R2 and R3 altogether, and it will give the exact same drop in the same current. This is due to Ohm's law, where V equals IR. For each resistor, we could sum these up, since in a series circuit all the voltages must add up to 5, so we can do V1 plus V2 plus V3 is equal to 5 volts. We then can take IR1 plus IR2 plus IR3, and then we can factor out this common I, and this gives us R1 plus R2 plus R3. So this is effectively our total resistance, and that tells us if we were to use one resistor of that size, we would get the same current out. So we're going to move over to our breadboard just now, and we're going to demonstrate this in action. Okay, so we've moved over to our breadboard now. What we're going to do is we're going to build a very simple series circuit, the same one that we've just drawn actually, with 3 resistors in series. We're going to begin, we're going to place our first resistor in columns 1 and column 6. Then we'll place our second in column 6 and column 12. And just as a quick side note, when you're making your own circuits, ideally you want to make the circuit as neat and tidy as possible. To make a very compact series circuit, I would connect this resistor in columns 2 and column 6. That way the resistors are kept very close together, and it just means that you're using less of the board overall. But just for the demonstration purposes, I'm going to use column 6 and column 12. Then finally for the third resistor, I'm going to use columns 12 and columns 18. And this is the very basics, of our series circuit. We have our multimeter handy here. We're just going to check the resistance of each of these resistors, just so that we can do a quick calculation to make sure everything is as it should be. So we'll take our first measurement of this resistor here. I'm going to hold our board steady and going to put our red probe on one side and our black probe on the other. and we get a measurement of 1,321. I'll quickly write that down so that we've got a note of it to do our calculation with. Then for our next resistor, we can do exactly the same once again. And this time we get a measurement of 1,303. So we will write that down, 1,303. And then for our final resistor, we will do the same once again. And we get a reading of 916 ohms. So once again, we'll quickly write down 916. And then we're going to move back over and we're going to do a quick calculation to determine just what the current should be in this circuit. So, as always, I'll turn my multimeter off since I'm not using it, and we're going to jump back over to our paper. What we're going to be doing is we are going to do a very simple Ohm's law, as we've got demonstrated to the left of our resistances here. So, I have my trusty calculator, and we're going to add up our resistances to get what RT is equal to. We're going to call RT our total resistance. So we're going to do 1321 plus 1303 plus 916, and our total resistance is 3,540 ohms. Since we are using our Arduino for our power supply, we know that V is going to be equal to 5 volts. So our current is going to equal V over RT, which is going to equal 5 over 3,540, which is equal to 1.41 by 10 to the negative 3. Since we're using currents, this is going to be in amps, and this is the same as writing 1.4 milliamps. So we're going to move back over to our board just now, and we're going to make sure that our calculation is correct. I'm going to connect our 0 volt line and our 5 volt line so that we can actually get a reading for our current. So I'll pop our 5 volt into column 1 and our 0 volt into column 18. As so. And now we have quite the nice connection point on our 0 volt line there. And so that we can connect our ammeter in series, I'm going to move the leg of this one here to column 17. And then we're going to take our ammeter. We're going to set this. We know that we're looking for something in the range of 1.4 milliamps. So we can set this to be in 20 milliamps. We've got to make sure that our cables are in the right ports. So we're going to move our black over from 10 amps to COM. And then we're going to connect our red to our resistor and our black to our ground. And as we calculated, we have 1.43 milliamps. This is very good. We now know that Ohm's law actually does in fact work. So next thing what we're going to do is we're going to discuss the parallel circuit. We're going to move back over to our paper and we're going to just see what parallel circuits do. Okay, we are now going to be drawing a parallel circuit. As always, we're going to start with our 5 volt power supply, and instead of adding them in series this time, we're going to add our resistors one on top of the other in a parallel circuit. We're going to begin. Here's going to be what we call a junction. This is where we can connect multiple wires to the same thing in a circuit diagram. So we had a junction on either side, then we're going to add R2 underneath, and then R3 underneath this. So this is a parallel circuit. We're going to add another junction on this one so that it shows that these connect. And then we're going to connect this up to the other side of our 5 volt supply. Just write 5 volts here. So again, using our traffic analogy, if you were the current coming along this bit here, you're going to hit these junctions going into each of these resistors. If one resistor is bigger than the other, you're going to be less likely to go through that one. You're going to choose the path of least resistance. So we'll label these as R1, R2, and R3. And what we're going to say is we're going to imagine just if this was the road you're coming along, and then you have 3 different paths you can take. If each one has a set of traffic lights, then what you're going to want to do is you're going to take the path which has the least traffic waiting at those traffic lights. At the end of the day, you all end up in the same place once again. And what we're going to be doing is we're going to call this path R1, this one R2, and this one R3. If the current flowing to R1 is equal to flowing to R2 and is equal to R3, that implies that R1 is equal to R2, which is equal to R3. This allows us to set up for dividing the voltages. Dividing the currents. What happens in a parallel circuit is that the voltage supplied to each rail here, here, and here, the voltage is exactly the same. So all three of these resistors get 5 volts. So that's to say that V is equal to I1 R1 is equal to I2 R2 and is equal to I3 R3. We want to calculate for the total current because the current splits in a parallel circuit. So if we label in here, this is I1, that's I2, and that is I3. We have our I total here, which I'll label as IT, and they all add up on the other side again to give us IT. So if we wanted to find out what IT is, we have to do I1 plus I2 plus I3. And using Ohm's law, we can see that I1 is equal to V over R1, I2 is equal to V over R2, and I3 is equal to V over R3. This tells us that we can then take out our common factor of V, and for a parallel circuit you get that your total resistance is 1 over R1 plus 1 over R2 plus 1 over R3, and then if you had more resistors in parallel, of course, you would just add them on. So what we can do is we can make our parallel circuit, and we will use this to determine if our current is in fact correct. So once again, I have the same 3 resistors that we just used in our previous examples. They all have the same resistances as we just measured, so there's no need to measure them once again. I'm going to begin. We're going to place into columns 1 and 6 for each of our resistors. And then what this does, by connecting them into the same columns, is creates our parallel circuit. As we described, it creates different paths for the current to take to get to the same place. So now all 3 of our resistors are into our board. We'll connect our 5 volts and our 0 volts. So here is a very simple parallel circuit. And then what we will do is we will measure our current just now. We will go to our 200 milliamps once again. We'll put 1 probe onto our resistor. I should remember we're connecting in series since this is an ammeter, so I need to move our 5 volt or ground volt, into a different column. So from this resistor to this part here, we can see that we are getting 12.9 milliamps. We'll then calculate just to make sure that this is in fact correct. So we'll move back over to our paper just now, and we will see what happens. And we are set up our sum using the equation that we just found. So we have our 3 resistances on the left hand side here, and we know that our V is going to equal 5 volts since we used our Arduino board once again. We'll set up our calculation, and once again I have my trusty calculator next to me right here. I'll place it in front, and we will write down our 5 times 1 over 1321 plus 1 over 1303 plus our 1 over 916. When we add up 1 over all of our resistances, we will get, I'll put this on to the calculator just now, 1321 plus 1 over 1303 plus 1 over 916. This gives us 2.616 by 10 to the minus 3. So we can write this in as 2.62 by 10 to the minus 3. And this will give us, when we multiply it by our 5, 0.0131 amps, which, as you can see, is 13.1 milliamps. This is slightly higher than what we measured, but it's within like 1 milliamp of the actual value. This is very good. It means that we can make a reasonable assumption that Ohm's law again does work. With all of this being said, that brings us to the end of our video. So thanks for watching, and in the next one we are going to be talking about the first of the temperature sensors, the PT1000, and another type of circuit development, the voltage divider. Thanks for watching, and I'll see you in the next one. Bye for now.